All right, I want to go over the cosine and the sine function. Something you already know, but from a slightly different perspective. All right, so here's how we define the cosine. The cosine is pretty well understood. Here we have a unit circle, and we create an angle. We call this angle theta, and we have that the cosine of theta is equal to the x-coordinate on this point on the unit circle, and the sine theta is the y-coordinate on the unit circle. That's all fantastic. Here, of course, the sine and cosine are nothing more than very specific function notation symbols. Instead of using the general f of theta of x, for example, I'm using cosine of theta equals to x. All right, let's see where this goes next. And again, I have now a GeoGebra applet going. And again, I have the unit circle, and here's my point. And right now I have it set to sine, put the trace on, and it says if the 0 radians, which equals 0 degrees, and if I look at the y-coordinate, it's 0. So the sine of 0 is 0. And if, of course, I move on the unit circle, as I change the radians, the y-coordinate changes, fantastic. So you know all of that. Here, for example, I'm going to reach the value of pi over 2, and sine of pi over 2 is 1. It's fantastic. You know all of that. The next question is, how is this happening? Notice we have you memorize some of these. We have you memorize what sine of pi over 2 is, what sine of pi is, what sine of 30 degrees is, what sine of 60 degrees is. We have you memorize these things. But curiously, we've never said to evaluate. And by evaluate, I mean the following. Well, it turns out there's no way to represent cosine, sine, tangent in a form that's finite. There's no way of doing it. We can define what the cosine is, we can define what the sine is, but we can't actually write down the equation that represents it. Now, if you take calculus, you will do this at some point in calculus, depending on the course you take in calculus. But we use some calculus technique to start to allow ourselves to represent, for example, here's the cosine, and it says the cosine of some angle can be represented, but here's the catch. There is a bunch of terms here starting to represent the cosine of whatever angle you put in here, but this series never ends. This goes up to infinity, which means there is no way for me to write down what the cosine of an angle is. So here's again a series that's trying to tell you that this is going to go on forever, infinite. And you'll notice, look, e to the x, the exponential e to the x. Notice I can do an exponential function, 2 to the x, I can do. 3 to the x, I can do, no problem. But e to the x, how do I do that? E is an irrational number. And it turns out, again, there's no way for me to write down how I will do that. And again, it's represented by an infinite series. And look, your old friend, the logs. Logs suffer from exactly the same problem. And that's why a lot of people, when they take Math 111 or college algebra, absolutely hate logs. And really what's happening is there's something that's bothering them, but it's never fully explained what's going on. And what's going on is that you cannot do just a nice algorithmic evaluation that gives you a result. It's always this roundabout way of getting something. There's not a direct way of doing so. And the reason, because we cannot write down with a log of a number. We know what it represents, but we just cannot write it down. Again, here I'm in Desmos. I've defined this function g of x to just be the cosine function. Now, of course, this is kind of ridiculous because I'm using function notation twice. The only reason I've done this is so you can see again that this is really truly function notation, nothing more. So for example, if I write g of pi, g of pi is -1. Cosine of pi is -1. So again, these two are tied together. Now, I want to show you how this works right here. How is a computer able to tell me that g of pi is -1? Well, there is some algorithm that looks like this effect, except, again, I mentioned this goes on forever, so a programmer cannot enter this infinite series into a computer algorithm. But we can add terms to get us a certain degree of accuracy, and there's other little tricks and maneuvers that may help us even shorten this up a bit. But I want to just prove to you that this can give us what's sitting here. So I'm going to go fast here. I'm going to stop the video and type in a few terms to speed this process. Okay, so I've typed the first 3 terms. 1, x squared over 2 factorial, x to the 4th over 2 factorial, and you see now how the graph is falling here, right over the sine function. It's still not perfect. This is just a polynomial. So you'll notice that the degree of this, the highest power is the 4th power, and you do have this polynomial shape taking place. So if I come over here, for example, just to kind of show you this, h of pi, for example, does not give me right now what I'm looking for. Okay, because I didn't add enough terms at all. If, of course, I type h of 0, that will give me exactly 1. What if I type here h pi over 4, that is 0.707. If I type here h pi over 4, look at that. Look pretty close, not exact, but notice to the 3 decimal places, it's exact, but not the 4th. And now if you look closely, you see the green line is draped over the sine function pretty close. I mean, I can't tell the difference right now. They're not right on top of each other, but to the naked eye, it looks like they're on top of each other, but they're not. So if I look at this, again, it looks close, but not quite. So here is, again, 0. Here's pi. Here is pi over 2, somewhere here. And over here. And so right around here is pi over 4. And you can see the 2 are very close. Let's add more terms and see what happens. Okay, so now I've doubled the number of terms. Before I only had 1, 2, 3 terms. Now I have 6 terms. And you'll notice if I enter h pi over 4, now I'm getting 0.7071067. Look at that, 678. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal place match. And now when I look at the sine function and this polynomial that's mimicking the sine function, you'll notice how much longer now this whole thing is draped over. Again, if I go to pi over 2, I'm not expecting an exact match. H pi over 2 is 0. What does this thing give me? Notice it doesn't give me 0, but it's telling me it's practically 0. Let me add a few more terms. So now again, I entered even more terms, and you'll notice how close the blue line is to the red line. The red line is whatever's programmed into Desmos. And you can see that it's able to generate that sine function seemingly forever. Or sorry, in this case, the cosine function seemingly forever. So the algorithm, how it's doing it, is different from what I have here. But it is in the same spirit. It's just that the algorithm might be more sophisticated. But you can see now that if I were to type, for example, h of pi divided by 4, I get this answer. Let's see what this other algorithm here generates. And you'll notice now when I type this, both are giving me exactly the same value to this last decimal place. But again, whatever is typed into Desmos, you can see that it's different because when I expand this, notice the blue line is what I've done. That's all I've done. while the red line is what Desmos says this function is, which is correct. So again, there's something else involved here, how it's generating this function. But again, it is a algorithm. There is no way for one to express this sequence. You can only do it to a certain decimal place, and that is all you're able to do. So these type of functions are called transcendentals, which all that means is I cannot express it in a finite number of, using a finite number of terms, just using arithmetic, adding, subtracting, multiplying, dividing, using again a finite number of terms. But this is why we need identities. Identities help manipulate the cosine and sine function because there's no way to do this algebraically. So identities are really necessary when you're dealing with transcendental functions, and that's why when you were doing logs, you use identities all the time. Now, when you took college algebra, they didn't call them log identities, they call them properties of logarithmics. But if you just type on the web list of logarithmic identities, you're going to get both the word identity and properties of logarithmic. And here they are. Here's your log identities. But again, you knew them as properties of logarithms.